Hi everyone, myself Dr. P. Ashok Babu. So in this video I am going to discuss about the convection and conduction current densities. Currents and current densities. First of all, we will see the what is a convection current and what is a conduction current. Then first we will define the different types of materials. After defining the different type of materials, we will define the conduction current and convection current, conduction current density and convection current densities. So here, as electric field can exist in free space, they can exist in material media. So materials are broadly classified in terms of their electrical properties as conductors and non-conductors. So non-conducting materials are usually referred to as insulator or dielectrics. Insulators or dielectrics. The conductivity of material usually depend upon temperature and frequency. The conductivity of any material will depend upon the temperature and frequency. A material with high conductivity, where conductivity sigma is very greater than 1, is referred to as a metal. Where one with low conductivity, it means sigma, the conductivity sigma is very less than 1, is referred to as insulator. Therefore, the metals can be mainly classified as conductor and insulator. So for conductors, the conductivity sigma is very greater than 1. For insulators, the conductivity sigma is very less than 1. A material whose conductivity lies somewhere between those of metals and insulators, or a material whose conductivity lies between the conductors and insulators is known as a semiconductor material. The conductivity of metals generally increases with decrease in temperature. The conductivity of metals generally increases with decrease in temperature. So let us assume at a temperatures near absolute zero. At absolute zero temperature, some conductors exhibit infinite conductivity and are called as superconductors, or a material which exhibit infinite conductivity are known as superconductors. So here lead and aluminum are the examples of superconductors. So they are the different classification of the materials: conductors, insulators, semiconductor and superconductor. So all the conductivity generally depends upon the temperature and frequency. Next. So electric voltage, or which is also known as a potential difference, and current are two fundamental quantities in electrical engineering. Generally, electric potential or electric voltage. Second one is a current, are the two fundamental quantities in any electrical engineering. So here electrical current is generally caused by the motion of electric charges. The current is generally caused by the motion of electric charges. The current through a given area is the electric charge passing through the area per unit time. Or we can define the current I is equal to the rate of change of charge, d by dt of charge will give the current flow in that particular area. So this thus in a current of 1 ampere, thus in a current of 1 ampere, charge is being transferred at a rate of 1 coulomb per second. Thus in a current of 1 ampere, let us assume a current of 1 ampere. In a current of 1 ampere, charge is being transferred at a rate of 1 coulomb per second. So if current, let us assume a current delta I. Delta I is the change in current. Change in current flows through a planar surface delta S. Delta S is the change in surface. Then the current density can be defined as where I is the current, where I is known as a current, J is known as a current density. I is the current, J is known as current density. So here current density means current per unit area. The current per unit area, I by A will give the current density. The current per unit area will give the current density. Therefore, the current density J is equal to delta I by delta S. Change in current by change in surface area. Therefore, we can express the term as delta I is equal to J into delta S. Delta I is equal to J into delta S. Assume that the current density is perpendicular to the surface. When the current density is perpendicular to the surface, then we can express the change in current delta I is equal to the current density J into change in surface area. Change in surface area. So here we can define the convection and conduction current densities by assuming a figure, current of a filament current. Let us assume a filament. Let us assume a filament. So in that filament, the total filament is placed along the y-axis of a rectangular coordinate system. So when we place a filament in rectangular along the y-axis of a rectangular coordinate system, we can define the convection current and we can define the conduction current. So here to define the convection and conduction current densities, let us assume a filament which is having the charge density rho s, which is having the charge density rho s. And to define the convection current densities, here let us assume a surface area. Let us assume a surface area delta s. Let us assume a surface area delta s, because we assume the total filament along the y-axis. So we have delta y. We have the current flow is along the y-axis only, and there is no current flow along the z-axis and x-axis. The total current flow will along the y-axis only. Therefore, we need to consider the change in y. And here we can define the current from the current density. From current density or from equation 3, we can, if we integrate the equation 3 on both sides, then we have I is equal to surface integral J into ds. So it means the current I is equal to surface integral of current density will give the current. So depending upon how current is produced, so there are different kinds of current densities. So there are three types of current densities. First one is the convection current density. Second one is the conduction current density. Third one is the displacement current density. So in our class, in today's class, I am going to define the convection current density and conduction current density. First, we will define the convection current density. So here the convection current density as distinct from conduction current density. Both convection and conduction are different from each other. So which does not involve any conductors. A convection current density does not involve any conductors and consequently does not satisfy Ohm's law, because it will not involve, it don't involve any conductor, it don't satisfy the Ohm's law. It don't satisfy the Ohm's law. Next, it occurs, the convection current density occurs when current flows through an insulating medium such as a rarefied gas or vacuum. Convection current density will occur when a current flows through a insulating media. When current flows through a insulating medium such as liquid, rarefied gas or vacuum. When current flows through these three areas, we can define the convection current density. So a beam of electron in vacuum tube. A beam of electron in a vacuum tube is the example of convection current. So because of the convection current, we have convection current density. Next, consider a filament, same as the previous circuit. So if there is a flow of charge density, let us assume the filament is having the charge density rho v at a velocity u is equal to uy into ay. Because the current flows along the y-axis, we can define the velocity in y-axis direction only, uy into ay. So from equation 1, already we have defined the current I is equal to the current I equal to is the rate of change of charge. Therefore, we can write the current delta I is equal to a change in I. Delta I is equal to delta Q by delta I. Delta Q by delta I. So here delta Q is nothing but the change in charge through in a filament. The change in charge in a filament. Here to find out the delta Q or to find out the change in charge, here we need to assume the total surface area of a filament and area of a filament delta S, and it flows along the y-axis. Therefore, the total charge is equal to the total surface area into surface area of that particular filament, and because it flows along the y-axis, we need to write the delta y. Therefore, delta Q is equal to, we can substitute rho S into delta S into delta y. Rho V into delta S into delta y by delta T. So that is the rate of change of displacement, rate of change of displacement will give the velocity Vy. Because it flows along the y direction, we have Vy. Therefore, it is rho V into, rho V is the volume charge density, rho V into surface area into velocity along the y direction will use the change in current. Next, the current density at a given point, the current density at a given point is the current through a unit normal area at that point. Current through a unit normal area at that particular point. So the y-directed current density Jy can be defined as, it can be defined in a similar fashion, same as the previous one. So therefore Jy is equal to change in current to the change in surface area. So in a simple way, are same as the previous current density. Here we can write current density J is equal to rho V into current density. So here we have delta I is equal to, it is rho V into delta S into Uy, or delta I by delta S. Delta I by delta S is equal to, delta I by delta S is equal to, here we can write, it is rho V into Uy. Delta I by delta S is nothing but the current density delta Z, current density delta Z, which is nothing but volume charge density into velocity along the y direction. Velocity along the y direction. Therefore, the current density J is equal to, or simply current density J is equal to rho V into V, where rho V is the volume charge density, V is the velocity. The current density can be defined as, it is a product of volume charge density into velocity. Here the current I is the convection current and J is the convection current density in amperes per square meter. Amperes per square meter. The units for the current density are amperes per square meter. So this is about the convection current density. Now we can define the conduction current density. So here in convection current density, it don't involve any conductors, whereas in conduction current density, it requires a conductor to transfer the for the flow of charge. A conductor is characterized by a large number of electrons that provide conduction current, due to an impressed electric field. So when, let us assume, an electric field E is applied. So when we apply an electric field E, we can find out the force on electric field by using the formula F is equal to Q into E. We know the formula, the force F is equal to Q into E. We know the formula for F is equal to Q into E. So by using the formula, we can find out the force on a charge. So here let us assume the charge Q is equal to minus E. Therefore, the force on charge is equal to, here in place of charge, we can write minus E into E. Therefore, the force on a charge is equal to minus E into capital E, where capital E is the electric field intensity, minus E is the charge of an electron. Next, since the electron is not in the free space, it will not experience an average acceleration under the influence of the electric field. Therefore, it suffers, so because of that, it suffers a constant collisions with the atomic lattice and drifts from one atom to the another atom. If an electron with mass m, let us assume an electron of mass m moving in an electric field E with an average drift velocity u. Let us assume an electron of mass m is moving in an electric field E with a velocity u. According to Newton's laws, the average change in momentum of the free electron must match the applied force. Therefore, the average momentum of the free electron, that is m into u by tau, where m is the mass of electron, u is the velocity of an electron, tau is the average lifetime of an electron between the collision, must equal to the force on electron. Here the force on electron is minus E into E. Therefore, we can express the velocity u is equal to, and if you cross multiply the equation, so it is minus E tau by mass into electric field intensity. where tau is the average time interval between the collisions, where tau is the average time interval between the collisions. So this indicates that the drift velocity of an electron, is directly proportional to the applied field. So E is here, U is directly proportional to E. We can write the velocity of an electron is directly proportional to the applied electric field. U is directly proportional to E. Next, let us assume there are n electrons per unit volume. If we assume there are n electrons per unit volume, the electronic charge density is given by where rho v is the volume charge density. Therefore, the volume charge density rho v is equal to minus n into E, where n is the number of electrons, E is the charge of an electron. Therefore, the total volume charge density rho v is equal to minus n into E. Next, here we can define the conduction current density as the conduction current density J is equal to, which is similar as previous convection current density. This volume charge density into velocity of an electron. So where the velocity of electron is rho v into, where rho v in place of rho v, we can write in place of electron, in place of velocity, we can write the U is equal to, we can write minus E tau into E by M, where E is the minus, small e is the charge of an electron, tau is the average lifetime before the collision, capital E is electric field density, M is the mass of an electron. So if you substitute U is equal to minus E tau by M into E, and so here we can write the volume charge density rho v is equal to minus NE. For minus N into E into here minus, we can write E tau by M into E. So minus cancel each other. Therefore here we have N into E square tau by M into E. Or therefore we can write in general J is equal to sigma into E, where sigma is the conductivity. The conductivity sigma is equal to, we have N into E square tau by M. Again, where sigma is the conductivity of an electron, N is the number of electrons, E is the charge of an electron, tau is the average lifetime before the collision, M is the mass of electron. For here, we can express the equation as the current density, the conduction current density, J is equal to sigma into E. The conduction current density J is equal to sigma into E, where sigma is the conductivity of electron, E is the electric field intensity. So the relationship here, this relationship J is equal to sigma E is also known as the point form of Ohm's law. The conduction current density J is equal to sigma E, which is also known as the point form of Ohm's law. So this is about the convection current density, convection current density, and conduction current densities. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.